This is PhD Alborz Seddigh Afshar, 20 May 1854, 20 May 2015, 1854 p.m. I'm going to invent some more. This invention 989 and further. Yeah, so I'm going to dice these forces. Then that's it. Yeah. So okay, I'm going to dice some 1, 2, 3, 4, 5 and inventions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. So I dice H R D. So H R D is H is height, R is resistance, D is diffusion, which is parallel to L and D is parallel temperature. So temperature is also a function of resistance. With temperature, resistance increases. So L and D is also diffusion is a function of resistance also. So temperature increases resistance, so diffusion L and D increases also with resistance, or resistance increases with temperature. So resistance increases with diffusion in effect. So because the resistance increase T is L and D. K times L and D, and H is height, and I think I'm going to say, in fact, resistance is a function of temperature, so I'm going to say L and D is a function of equals resistance times a constant. Height is the length of the height over which something diffuses, also increases decreases the diffusion constant. The diffusion decreases over a tube with the distance of the tube. The diffusion decreases, so it's indirectly proportional to height. I'm not sure if it's quadratic or not, or to what extent that was that. So I would say L and D equals R divided by H times flow constant. Okay, that's it. I'm not sure it's H squared or H to the power of something, or R to the power of what, so I gotta check that. I think I had a book on that, on temperature and resistance. I think it was R temperature to the power of something, so it's R root of to something, so it's proportional to these things. I'm not sure to what power of them. But I would say, as a general rule, I could look that up, the function of resistance and temperature and height. But I would say if you want to use that in a situation where you involve diffusion, what would involve diffusion would be, for instance, if you want to store something for long term, store a liquid, and you don't want it to diffuse. You would, for instance, want the resistance, if you're storing a certain charge, for instance, in a different type of diffusion as a gas type diffusion, but you're storing charged particles in type of, for instance, fusor, and you want it to not diffuse out of the fusor, you got to increase the resistance and of the fusor by increasing the wall's charge and height, so the distance it's got to travel through the fusor. So the larger fusor causes for less diffusion of the charged particles out of the fusor, so it's got to be very charged, extremely charged, and also very large fusor. Small fusor probably causes a larger diffusion, gets out more instead of a large fusor. So larger volume of the fusor in effect, so the height or the radius is increased in that sense, so the volume is increased too. So that would be the physics. How I would involve that in embryology. For instance, a fusor in embryology, I would say a fusor shaped like the images I have on my blog, shaped like genitalia. So I could involve two fusor balls that are interconnected with a tube that there's fusor. It's a two fusor balls with a tube interconnection, in which at the central part of the tubing the plasmas collide. So that relates to embryology. It looks like genitalia in effect, in which from the two testicles to the seminal ducts, the semen mixes with the seminal fluid, the sperm mixes with the seminal fluid. So I would say you could have like barbell, two large volume fusors with a cylindrical interconnection part in the center where the charged particles can get out and they start colliding within in the tube. So that's genitalia-like, anatomy-based embryology-like embryology combined with physics. So I had the fusor, then I had the force, then I had the embryology. So now I would say above exponential and linear production of these things, and also arrays of them, which cause parallel couplings and serial couplings of these things, of these fusors. Linear exponential and above exponential, first to 500 exponential and above exponential and linear. So that would be 6 together, so that would be around 6 ideas for the first set of 6. That's it. Of 800, then force, fusor, embryology, exponential, above exponential. You could also have the single fusor. Now see the embryology fusor. So I already had the force, the fusor, the embryology, multiple fusor, anatomy like multiple fusor. I would say in embryology, it can you can have a fusor unit fueling the rocket pump in effect, and the embryology unit and the embryology hospital. So you would have a separate power generation through a fusor in the hospital without storage of power. Let's say the power goes out long term and they haven't got the power to refuel the hospital. So it would be fusion driven hospital. So that would be, I would say at that point does hit the 6th idea. So it starts being 6 ideas for the series of it. That's it. And if you don't want to count each of the 500 exponentials and linears and above exponentials, that's a separate idea. Which someone might, at that point you might cut 500 of these, but I don't think they actually do that. So it wouldn't necessarily consider that much innovation. Maybe it would be to a dumber judge. I suppose that might find surprising. So the smarter get the judges, the less stuff is considered surprising later, or some type of new innovation.